Hi, this is Justin Mansell from Active Optical Systems, and this is a quick video to show you how to measure the diverging radius of curvature of a wavefront from a fiber tip. So I'll start with some of the setup prerequisites, talk about our optical description, and then jump into software usage. You can download our software from the AOS website and install it using the installer. If you're using a PoE camera that's power over Ethernet, you will have to have the PoE injector installed or have it plugged into a switch that provides PoE. I'm using a USB camera today, so you won't see that PoE injector in my optical setup. You'll also have to have a software key installed in your computer. The optical setup you're going to see here today involves a fiber tip going through a piece of beam tube, and I'll take this collimating lens on and off. It'll stay on for calibration and then come off as I'm trying to measure the diverging curvature. And then down here I have a wavefront sensor that has a approximately 40-ish millimeter focal length lens array, 500 micron pitch, and this is a USB camera. It's a Mako U29B camera. Now to the software. Okay, so this is the AOS software loaded up. This is a very low resolution wavefront sensor. It was actually designed to be high sensitivity and very low resolution. This is a live view of the optical setup where we have the wavefront sensor here, and this is the collimating lens and the fiber tip back here. So what I'm going to do today is start with the collimating lens in place and hit continuous acquire. And you can see I've got a pretty good array of spots on the camera. I've not saturated the camera. The histogram looks pretty good. So what I'll do is, since I have already checked it with this shear plate here, I know it's approximately collimated going in, and I can just say create reference. And so now it'll recreate this reference for me, and I can go into continuous acquire, and you can see I'm getting noise. Essentially, how much noise? Let's stop and see. It's on the order of a nanometer of noise. Again, this is a very high sensitivity wavefront sensor situation. So next I'll remove the lens from the fiber tip and stop the collimating process. So now the lens has been removed, and I can go back to continuous acquire here. By removing the lens, I've made the intensity much lower, as you can see here. In fact, so low that it can't even really see the spots anymore. So I'll go to histogram mode again and turn up the power on my fiber until I get, yeah, that looks pretty good. Let me stop this. The other thing I want to check is I want to turn off subtract average tilt and take a look at how far tilted I am. I have a little bit of tilt on this, not too bad. I can go in and tilt the wavefront sensor in order to try to remove some of that tilt. That's good in that axis, and now I'll go to the other axis here. Oops, wrong way. And now I've got the tilt removed. The reason to do this is that it gives you the maximum dynamic range out of your wavefront sensor, meaning that when I look at this image here, the spots are split in their motion from the center. They're moving, basically symmetrically about this, and so that gives me the most dynamic range. So I've turned on subtract average tilt and continuous acquire, and I'm getting this nice curvature term coming out. It's hard to make out this ruler in the video, but the lens array is approximately, call it 48.5 centimeters from the fiber tip. When I go into the analysis tab, I can see here that it's predicting 48.2 centimeters from the fiber tip. And I'll put this in continuous acquire mode for a moment here, and what I can do is slide the translation stage. And so you come down here, just manually slide it to the other end of its position, and it's saying 50.9 and back to 48.2. So you can see I can measure that distance from the lens array to the diverging source, the diverging fiber tip, by just moving this around. My only concern with this is that this translation stage isn't quite lined up with the axis of the diverging beam, because as you can see here, I'm very close to the edge on this. Not terribly, I mean, not enough to be ridiculously concerned, but now I've centered it back up. So I've got a bit of a tilt problem going on there. Let me do this, let me stop this, and I can show it a little better by not subtracting the average tilt. So it looks okay here, and then as I push this around, you can see that I'm tilting it as well. So I've got a little bit of a misalignment gap there. But we were seeing, 48.2 centimeters, and it was going to 50.8. And so this is about what I would expect for the motion of this translation stage, which is about a 1-inch translation stage. So it should be about 2.5, and so 48.2 plus 2.5 is 50.7. Yep, that's perfect. So you can see here I can use the wavefront sensor to measure the radius of curvature coming out of the tip of a beam coming out of the tip of a diverging fiber here. So this gives me a pretty accurate measurement of where the position of the wavefront sensor lens array is relative to the tip of the fiber. That's it for this video. Thank you so much for watching, and if you have any questions, don't hesitate to contact us at the Active Optical Systems website.